Good morning, guys. Happy Thursday. We're going to be talking about section 5.6 today, which is about inverse trig functions. If you did not have the supreme pleasure of being in Miss Morton's trig class, then I'm sure you have no idea what you're talking about. And if you were in Miss Martin's trig class, you may still have no idea what you're talking about because it's been a year. Who knows? So we're going to talk a little bit about some big definitions, some terminology that comes up when it comes to trig functions specifically. And then finally, one of the big things we're going to talk about is how to use this in terms of calculus. This is one of the last major sets of information we're going to be discussing in our time together. And we're, as always, going to go with both parts, which is going to be the differentiation and then the integration. Now, the differentiation is today's material. Tomorrow we'll talk about integration, and tomorrow is the last section. So be keeping that in mind as we're going forward. So let's start talking about inverse differentiation for trig functions. All right. First thing to mention, the definition of the inverse trig functions. So we've already talked about what an inverse is. An inverse, by our definition, was any function, we'll call it g, such that if we plug g into f, we get out the linear constant x. And if we plug f into g, we also get out that same constant function. This is the definition by standard metrics of an inverse. It's a function that undoes something else. So common inverses we've talked about were things like x squared and the square root of x, or x cubed and the cube root of x. And then more specifically, the one we talked about most recently, the natural log of x and e to the x, and then base a of x and log of a of x. And so each of these are inverse functions, just different kinds, because each one allows for us to plug one into the other and get back to x. If I plug x squared into the square root of x, the square and the square root will cancel, leaving x behind. If I plug the square root of x into x squared, the square and square root cancel, leaving x behind. If I plug the natural log into e, the natural log and the e will cancel, leaving just x behind. And if I plug e into the natural log, the e and the natural log will cancel, leaving just x behind. These are inverse functions. Now, every function in mathematics is supposed to have an inverse, provided that it meets a few properties. But there's one function we've talked about that hasn't had this happen. And these are trig functions. And so the first thing I want to note is this big table right here. The definition of an inverse function. So these don't have fancy names. Like, it's not like natural log and e, or a and x, or squared and square root. In many ways, it's more like this one. Because in many ways, these are named just like these are. We have x squared and we have the square root. We have x cubed and we have the cube root. In the name tells you that you're using the same function, just in the opposite way. Well, we have arcsine, arccosine, arctangent, arccotangent, arcsecant, and arccosecant to represent the inverses of each of these functions. So, these are by definition an inverse. So, if I was to write something like sine of arcsine, they're going to cancel because they're inverses. Arcsine and sine are natural opposites. And similarly, if I was to write arcsine of sine, they are also going to cancel. They're inverses. Now, by definition, if we know something like sine of x is equal to y, then by definition, arcsine of y should equal x. And so this is the other definition of an inverse, is that you basically flip around which one goes where. So originally x was in the function and it outputted y. Now y is in the function and it outputs x. Furthermore, and this is the big caveat to today, because we already know sine of x as a fraction. Sine is equal to opposite over hypotenuse, which means that arcsine will take in the opposite and the hypotenuse and output the angle. That's a big detail. So the way these in functions work is I input the angle, I output the fraction, but when we do an inverse, I input the fraction and output the angle. Now we did some of this in geometry, very, very little, but we did talk about it. Remember when we talked about inverses, one of the other ways to write an inverse is as f negative 1 of x. Now, when we talk about inverses of trig functions, you can talk about arc sine, and this is the more common one, but on some calculators and in some texts, you'll see sine negative 1. This is not the same as sine x to negative first power. These are not the same. Not in any way, not in any form, not even close. Okay? They're not the same. Sine inverse in this case just represents arc sine in shorter form to save some handwriting. Same with arc cosine. And the rest of them. Now, just real quick, to bring it up, depending on the calculator you may have arc sine or you may have sine inverse. If you're looking at mine, for example, which is my nice TI-84, boom, you'll notice that right here on my TI-84, I have sine, and then above it on the little calculator under the second command, I would have sine inverse. So if I wanted to do, for example, sine of 30 degrees, I would type in sine 30. But if I wanted to do the inverse, I would hit second and hit sine inverse. And so for this one, I have to type in the opposite and the hypotenuse as a fraction, like 3 over 5. And it would output the angle. For today, since we are going to be talking about trig functions, make sure to double check that you're in the correct mode. And for most of the problems today, we're going to be dealing with radians. So make sure you are in radian mode. If you're not, make sure to fix it. Okay. Next. It's important to note that when we talk about these functions, that they are also graphable. And so these are the 6 different graphs for these functions. So this is the graph of arc sine. And notice that the graph of arc sine looks like it's the graph of sine just turned. In fact, if I was to pull up that graph one more time, and go to the graphing tab, you'll notice that, remember, sine of x is a function that continually repeats. It's a function that over time oscillates back and forth. Whereas arc sine, if I do that one, give it a second, there we go. If I do arc sine, so I do sine inverse of x, so arc sine, its graph, you notice, is restricted. That is because the restricted version of this graph, you want to make sure when you talk about this graph, because in order for it to be an inverse and to be a function, it has to pass the vertical and horizontal line tests. Well, if we were to actually invert the entirety of sine, it wouldn't pass the vertical line test because the original function does not pass the horizontal line test. And so you can see in this picture, like, it's been restricted to be in this specific domain. Let's zoom in a little bit. So I'm going to change my Windows settings to -1 and +1 for x. And for y, -1 and +1. Actually, I think for y, I need to do, negative pi over 2. So negative pi over 2 and positive pi over 2. Okay, let's go to the graph. So you can see in blue here the sine function, and you can see in red here the arc sine function. And just to re-illustrate the point, remember the definition of inverse is that it should be reflexive across the y equals x line. And so if I put that line in here too, in black, notice that it seems to split these two functions evenly in half. So it seems to be up and down for the same amount, or at least there should be. Okay, it could be some imperfections in the graph maybe, but they should be inverses of each other. So this is the definition of an inverse, and these are the 6 graphs of them. Here they are. Note again the domains, the restrictions on these, because that can be a big play into how the functions interact. But the big one is to understand how they kind of work together. Okay, now we're going to talk about evaluating. And to evaluate these, I'm actually going to go to some examples from the text. So let's go ahead and look at some homework problems. So how do we evaluate? I'm going to start by looking at numbers 6 and 10. Okay, let's go to homework. Okay. The function asks for number 6, what is the arc sine of 0? Well, in order to answer a question like this, one of the best things you can do is convert from inverse into standard function notation. Because if we can understand this as sine, then I can understand it as arc sine. And so when a question asks to evaluate an arc trig function, one of your options is to convert into sines, cosines, tangents, and the other 3 as well. For this problem, I'm going to take this function and I'm going to rewrite it using my definition of arc sine. So my definition of arc sine, and I'm going to use this definition right here, arc sine of y is equal to x. So I'm going to assume this is equal to a number. I'm going to call that number x. What that means is if arc sine of 0 is equal to x, then that means sine of x equals 0. Now, how does that help me? Well, in this case, now I can use the unit circle. Because I can use the unit circle, and for this I'm just going to pull up a simple unit circle from Google. There it is. So, what this means is, where is sine equal to 0? Now, if you look in this graph and in this picture, remember, sine is interpreted as the y values, whereas cosine is interpreted as the x values. So in this list, I can see that that occurs twice. Once at 0, and this is 0 in both degrees and radians, of course, and then again at pi. However, the big trick when it comes to looking at the unit circle is make sure you are domain restricted. When you look at the unit circle, you are restricted by the domain of the function. And so now I'm going to go back to the text and showcase what piece of the text is really important here. Because in these functions, if you don't maintain the domain, you lose track of some of the answers that shouldn't be answered. So if you look at this, it says right here, we're dealing with arc sine. Arc sine is restricted between -1 and 1. Yet I just told you my answer is either 0 or pi. Pi is not inside that domain. So I'm actually going to get rid of pi, meaning the only answer for number 6 is 0. I get 2 answers from the unit circle, but remember, my domain is heavily restricted because we're dealing with a function. A function, meaning it has to follow function rules, meaning it is bounded in this case. So, notice how I did it. We converted into sine, cosines, and tangents. We used the unit circle to figure out what solution should work, and then we check the domain to see if any of those disappear. Let's look at number 10. Let's see if we can follow those same steps. And so I'll pull up my unit circle again here in a moment in order to help answer it. But until then, let's go ahead and look at number 10. Number 10. It says arc cotangent of negative square root of 3. Okay, so what does this mean? Well, I can rewrite this using sines, cosines, and tangents. Now remember, first thing I can rewrite, well, this is arc cotangent. Well, that means that this is going to be equal to x. And if that's the case, I can use my definition from my notes, which allows me to convert arc cotangent of a number into just cotangent. This becomes cotangent of x equals negative square root of 3. Now, if you don't have your unit circle fully memorized, this can be a really tough one to answer. But remember, you always have the option to convert into sines, cosines, and tangents. That's what I'm going to do. Remember, cotangent is just 1 over tangent. Sorry. Cotangent is literally 1 over this. So this will be negative square root of 3. I'm jumping ahead. And then what I can do is, if I can flip this side, I can also flip the other side using inverse properties. So in other words, tangent of x is equal to 1 over the negative square root of 3. Now, tangent is not typically given on the unit circle. However, remember, to do tangent, you can just do sine over cosine. So we can do sine divided by cosine equals 1 over square root of 3. So, in other words, where's a place where we end up with this relationship? It turns out that happens at 5 pi over 6. Oh, do I have that backwards? Nope. Make sure you read your table correctly. 2 pi over 3. Remember, it's sines divided by cosines. Maybe I can zoom this in a little bit. There we go. Okay. Remember, it's y's divided by x's. So, you know what? I had it right. It helps to have your unit circle memorized rather than trying to figure it out from here. I would recommend, if you don't know which of these actually works, do what I'm doing. Test them. See if any of these get this relationship. What is 1 over the negative square root of 3? In fact, we could do it with the calculator instead. So here's my calculator. So I could just try it out by hand and say, what is 1 divided by the square root of 3? Well, I should get negative 0.577. And then I could test out these answers I'm getting. Well, what about tangent of 5 pi over 6? Does that give me negative this answer? Yes, it does. So 5 pi over 6 works. There's one other number that gets it as well. And it should be, let me see if I can find it. Unit circle. And the other one should be right here, 11 pi over 6. These are all considered to be acceptable solutions, but now I need to double check my domain, see if it actually does work. And it turns out for these ones, it really doesn't. So let's go to my domain. In my domain, I'm looking at arc cotangent. It says, oh, any number works. So it turns out both of these should be good solutions. So there we go. Keep in mind for these types of functions, these types of problems, you may end up with more than one solution because there may end up being more than one place that has its answer. So make sure you get that as your property. So there we have it. Okay. That's the first piece, just evaluating. Unit circle can be very helpful here. There is a secondary part of evaluating, which has to deal with actually using, a triangle. So this is the first technique, is if you can convert it into sines, cosines, and tangents. Like that's option number 1 when possible. Option number 2, if that fails, make a triangle. And this is where if you've had trig and you remember trig, it's really helpful. If you haven't had trig, or you've forgotten your trig, or you didn't learn it the first time, then the second one can be a little bit tougher. So I want to look at number 18 and 20. So let's go to 18. And there's a good example of doing this right here with example 3. It works great for this kind of problem. Okay. Let's go to number 18. Number 18 states, find tangent of arc cosine. So here's the thing, like the big detail. These two don't interact well, like by themselves. And so one of the things you can do is you can write arc cosine as a triangle. So let's look at number 18. What have they told us? We want to do tangent of arc cosine of square root 2 over 2. Well, what does this mean? Well, it means that this means I have a triangle with some properties. What are those properties? Well, remember, you can always rewrite arc, cosine, and a function in terms of opposites, adjacents, and hypotenuses, just like you can do it with sines and cosines. And so what this means is I have a triangle whose adjacent is equal to the square root of 2 and whose hypotenuse is equal to 2. Because remember, I have arc cosine of square root 2 over 2. Well, arc cosine uses adjacent and hypotenuse. Arc cosine would use both those inside of it. So this tells me that I would have a triangle in this problem with an angle, which I'm going to call x, whose adjacent is the square root of 2 and whose hypotenuse is 2. This is one of the tricks you can do, is you can make a triangle. Just make sure it matches what you've been given. We've been told arc cosine of square root 2 over 2. Well, if square root of 2 over 2 is inside of a cosine function, that means we have an adjacent and hypotenuse. Adjacent and hypotenuse. Now, if you're going to make a triangle, the second thing you need to do is find all the sides. This trick uses Pythagorean's theorem. So in other words, a squared plus b squared equals c squared, where c is the hypotenuse, and this allows me to figure out this missing side. So I can do square root of 2 squared plus b squared equals 2 squared, or 2 plus b squared equals 4, b squared equals 2, so b equals the square root of 2. So this tells me, in my function, that I have this triangle in the problem. This triangle is the one created by arc cosine of square root 2 over 2. So again, the inner piece tells me to make a triangle with this property, where the adjacent is square root of 2, the hypotenuse is 2, and because of that, we can find the missing side using Pythagorean's theorem. Now, here's the thing. This asks for tangent of this triangle. If you remember your trig functions, tangent is equivalent to opposite over adjacent, which, if you look at this picture, if we have our angle, x, the opposite would be square root of 2. The adjacent would be square root of 2, meaning the tangent of arc cosine of square root 2 over 2 is equal to this fraction, square root 2 over 2, which is 1. So note, on ones like 18 and 20 that we'll do as well, this inner information tells you to build a triangle. It tells you how to build that triangle. Let's look at part B for 18, and then we'll do number 20 as well. Part B, it says we have cosine of arcsine of 5 over 13. Remember, the inner piece tells you to make a triangle. We're going to make a triangle with these properties. So when you make a triangle, you can make any triangle you want. It doesn't have to be to scale or anything. Because remember, this is all just scratch work. And so here's my angle, x. And what's sine? Sine is opposite over hypotenuse. So arcsine will have the opposite and the hypotenuse in it. Which means that my opposite side should be 5. My hypotenuse should be 13. Using Pythagorean's theorem, I can figure out the missing side. A squared plus b squared equals c squared. I know my a should be 5 squared plus b squared equals 13 squared. 5 squared is 25. B squared is b squared. 13 squared is 169. So that means b squared equals 144, or b equals 12. Which means that my missing side up here, my b, is 12. So the question asks, what is cosine of this triangle? Well, if I look at this picture, remember cosine is equal to adjacent over hypotenuse. We used arcsine to build a triangle, and then we're now using the triangle to evaluate the cosine function. So, the question asks, what is cosine of arcsine of 5 over 13? Well, it's just the cosine fraction for this built triangle, which cosine, remember, is adjacent over hypotenuse, so that'd be 12 over 13. Notice how we use the arcsine to define a relationship we already know, opposite over hypotenuse. And then we use the opposite over hypotenuse to create a sketch triangle. And then use that sketch triangle with Pythagorean's theorem to find the missing side. And then with that missing side, we can then find cosine. This statement right here, allow me to write this as a mathematical statement in words. It's kind of wordy, but here we go. This question is asking, what is cosine if the sine relationship is 5 over 13? Remember, arcsine is defined as the sine relationship between the ratio of the sides and the angle. So this will pop out an angle. And then we're just doing cosine of an angle. But in fact, the angle that's going to pop out is this one. You can actually do all of this with a calculator, but you'll usually get a fractional or a decimal answer, and you will oftentimes miss the easy fractional answer. And it's pretty easy to tell when your answer is being done with a calculator. So for example, if I was to come in here and pull up my calculator, I can actually type in cosine of sine inverse of 5 over 13. And it will give me an answer. And it turns out that answer is 12 divided by 13. But, you know, we math teachers are smart. We know you should get 12 over 13. If you write down 0.923 and don't show any work, we assume you did it in the calculator, and we're not going to give you any points. We're not stupid. Okay? Use that information as you will. You can always check your work with a calculator, is what I'm really saying. So, there are a couple questions that do ask you to actually do it with a calculator. So if you look here, for example, use a calculator to approximate the value. Use that, okay? Make sure it helps you. All right. This ability to build a triangle using the information you're given in Pythagorean's theorem is used quite a bit on 17 through 33. You will use this type of function and problem to solve questions from 17 through 33. And so I will also do number 20 real quick, just to showcase how it's done. And then we'll talk about the derivative part, the actual calculus. Yay! Let's do number 20. Actually, instead of doing 20, I might do 27. Or 28, I should say. Because we haven't done one like that yet, and I don't want to skip one of those, because those are pretty tough if you don't know what you're doing. So let's take a look. Well, here we go. It tells me we have secant of arctan of 4x. Now, because we have something inside of a trig function, we can think of this as arctan of 4x is going to be equal to an angle. Which means that if we flip-flop them, it would tell you that tangent of that angle is equal to 4x. Which means I can start building a triangle. Here's my angle. Okay. Well, what's tangent? Tangent is opposite over adjacent. Well, this is a fraction. I don't have a fraction over here. So one of the things I can do, of course, algebraically speaking, I can turn this into a fraction. Which means I now know my opposite side should be 4x, and my adjacent side should be 1. And just like before, how you can sit there and use Pythagorean's theorem to find the missing side, we're going to do it again. But this time we're going to have an x in there. Here's the big detail. We are not solving for x. So on questions like 28, you will not solve for x at all. X will just be floating around your problem. You won't know what it is or how it works. It's just there. Okay? So, what does my Pythagorean theorem say? It says a squared plus b squared equals c squared. So, everywhere there's an a, I replace with 1. If there's a b, I can replace with 4x. And then c squared is that missing side. So, 1 squared is 1. 4 squared is 16, x squared is x squared, equals c squared. I'm going to get c by itself is equal to 1 plus 16 x squared, which is our missing side is the square root of 1 plus 16x squared. Now the question is asking, what is secant in this triangle? Well, remember, secant is equivalent to 1 over cosine, or secant of an angle is equal to hypotenuse over adjacent. And because secant is equal to hypotenuse over adjacent, we know that the hypotenuse is the square root of 1 plus 16x squared, and the adjacent is 1, which means secant of the arctan of 4x is equal to, simplified, 1 plus 16x squared. Notice how we use the problem to define a triangle using the relationship. Then we use the triangle to find the missing side. Then we use the triangle and the missing side to define the relationship it asked about, secant. So they gave us arctan, which we used to build a triangle. We used Pythagorean to find the missing side. And then with the triangle fully completed, I can now answer the question, what on earth is secant? Well, secant is this. You'll use this a lot for 17 to 33, this process. So make note of it. You find the missing, you set up a triangle. If they haven't already given you one, notice that for some of them, they've already given you a triangle. Make sure you find that missing side. And then from there, we can just do each trig function with this triangle in mind. I'm sure this will be one that we have some questions on, but for now, I'll go ahead and put a pause there. And let's now talk about derivatives. Now, for these ones, the derivative rules are pretty short and sweet. Here they are. So, Theorem 516. Last piece of notes for the day. So you notice relatively short notes, but a lot of concept here. So, Theorem 516. And these are all your derivative rules. So this would be the derivative with respect to x of arc sine of u. And then we have equal to u prime over the square root of 1 minus u squared. I'm not going to bother writing out the rest of them. You probably should if you're doing your homework, or at least keep a thumb on this page, because you can use it a lot. Or, the better one, here are all of them, like make note of them, but really you might want to put a bookmark here. This is your big derivative list. This is every derivative we have talked about so far, done in U form, so in case the top piece is more complex or the inside pieces are more complex, this is the big derivative list. And so when you come across a question that asks you, okay, well, how do you do a product? Well, number 3 tells you how to do a product. Oh, what if it's, something to an n power? Well, whatever that thing is, here's the power rule with a chain inside of it. And so this really does showcase all the rules written out as much as possible. Now, it doesn't cover every possible case, because that'd be impossible, but it does get 99% of them. Okay? So let's talk a couple derivatives before we finish today. These ones, let's look at a few more problems. I'll reference back to that page quite a bit because I don't have these memorized, and I don't require you guys to either. So let's look at ones like 44. Well, what does 44 say? It says we're going to find the derivative of the function, and the function in question is f of t is equal to arc sine of t squared. Well, in this case, I have to recognize that this is arc sine of u when u equals t squared. Which means that if I go to my formula list, it tells me on the previous page that if I want to find the derivative of arc sine, it is u prime over the square root of 1 minus u squared. So this is f prime of u is equal to u prime over the square root of 1 minus u squared. Well, if I want to find f prime of t, all I have to do is everywhere there's a u, I plug in the u's, and everywhere there's a u prime, I would plug in 2t. So this is 2t over the square root of 1 minus t squared squared, or 2t over the square root of 1 minus t to the 4th power. And that's 44. Simple as can be. These ones are just plug and play formulas. You just got to know the formula and how to use it. 50. Of course, it's never that easy, right? You guys know this is calculus. So usually the harder ones are when they combine together multiple different things. So let's look at 50. 50 says we have h of x is equal to x squared times arctan of 5x. Well, in this case, I have a product. That product is really key. So what I'm going to do is I'm going to do the product rule. The product rule states we would do left times the right's derivative plus the right times the left's derivative. Well, let's answer these parts. X squared is just x squared. Arctan of 5x. Well, I go to my list. Arctangent is right here. It says u prime over 1 plus u squared. So this would be u prime. So the derivative of 5x would be 5 over 1 plus u squared. Well, my 5x would be my u. So 5x squared would be 25x squared. Plus arctangent of 5x is just arctangent of 5x times the derivative of x squared is 2x. It's common to put it in a correct form, so that's what I'm going to do. This would be h prime of x. Okay, so I'm going to move the x squared on top, so we'd have 5x squared over 1 plus 25x squared. There's no way to simplify that. Plus, we'll move the 2x to the front because we like having the variables come first, and then the expressions come last, so arctan of 5x. There it is. Notice again how I was just taking the things we just learned and applying them using old rules. So this was, in fact, number 3, which is the product rule, combined with the arctangent rule. Okay. We'll do one more, 58, to kind of combine together pieces from different sections. All right. 58. The last couple of problems deal with tangent lines. We talked about those a couple times in this chapter. Just remember, to do a tangent line, you have to find the slope. So use the derivative and then plug your x value in. 58, we have y equals x arctan of 2x minus 1 over 4 1 ln of 1 plus 4x squared. This is using a lot of rules from the different sections. Okay, so we have a product on one side. Subtraction means we can split this into two derivatives, and then on the right hand side we have natural logarithm. So let's do it one piece at a time. All right, the product. So I'd have left times the derivative of the right plus right times the derivative of the left. So that's this first piece. The second piece, I would do minus 1/4. Okay, the natural log, remember, becomes u prime over u. So u prime, so I take the derivative of the inside, 1 plus 4x squared would become 8x, because remember the 1 would drop. Power rule would say the 2 comes to the 4, becoming 8x. And then on bottom, we'd have 1 plus 4x squared, u prime over u. Okay, well, let's write our solutions here. So arctan of 2x, we would have as x times 2, which is u prime, over 1 plus u squared, so that'd be 4x squared, plus arctan of 2x times 1 minus, okay, the 1/4 and the 8 are going to cancel, meaning I have 2x on top over 1 plus 4x squared. Oh, look at this. This is going to be pretty cool. Look at this. So this first term becomes 2x over 1 plus 4x squared plus the arctan of 2x minus 2x over 1 plus 4x squared. And because of how this function worked out, we have a positive and a negative of the same thing, which means for this function, the final solution is arctan of 2x. So in other words, the derivative of this nasty equation is actually this fairly nice equation. That's pretty neat. But notice how we just take new rules and put them into problems where we have to use old rules too. And that's pretty much the entire section. So there's a big mix between questions involving those that are just using the inverse relationships. Note, building triangles was big. So this process right here, building triangles using the information they gave you and then using those triangles to answer questions. And then being able to take the derivative is the secondary part, the part that I care about more, if I'm being honest with you. So that'll be it. I hope you guys have a good rest of the day. I'll be posting the next section tomorrow, and otherwise, I'll see you guys then.